Hello, and welcome to my fifth video describing the Kinome Toolbox. In the previous videos, we have focused on the basics of Kinomics, the basic navigation of this toolbox, all of the level 1 data, and now we're moving on to the level 2 data. The level 2 data is very similar. There is level 2.0.1 and there is level 2.1.2. All these mean is that the 2.0.1 came from the level 1.0.1 data, and the level 2.1.2 data came from the level 1.1.2 data. However, the same analyses are applied to both of them. For comparison purposes, we're going to go ahead and open up both of these. The reason we've chosen to do this in this manner is because the methods we're applying for this background normalization are very unique and have not been utilized previously. So we wanted to show whether or not the background normalization was a good process. When we scroll over here, we're going to have two types of data. We're going to have the level 2.0.1 data. Please give this a moment to load. This is a large data set, and it is loading dynamically. You can see that it's already loaded here, but if the analyses haven't shown up yet, it's probably because the data is still loading. If we scroll over to our data tab, we can see that we still have our groups intact, and our analyses available here. So, our analyses available are ANOVA, reproducibility, heat map, and measurement reproducibility. These are all going to be based, at least loosely, on the analytical groups, which in theory should be technical or at least biologic replicates. In this case, they are technical replicates. If we move over to the ANOVA tab, what we see is another peptide picker. In this case, we can see that no peptides have been picked. So we have some options here as far as what's going to display. But in order to actually display any information, we need to pick a peptide. So this is where this search can come in handy. If I was really interested in the Sarc protein, I could go ahead and find the Sarc protein in this list. However, this is colored for things that have differences versus things that have very little differences. So I'm going to go ahead and select something that I know has a difference. If I scroll down, what I can see is the ANOVA results. In this case, we're looking at the slope of the line that's generated by varying the exposure time of the camera at the post-wash cycle. And then for the kinetic information, I'm looking at the exposure time of 50 milliseconds as taken throughout the entire reaction. And what I can see is the grouping creates a difference. We can see that this group 2 has a much higher value here than these other two for this particular slope. And if we were more interested in this, we can click on here and we can actually load in just the visualization of this very specific array. So moving back to here, we can see this is Paxi, P-A-X-I. So we can find this peptide. And it's going to be one of these two. It is Paxi 24. So we can see Paxi 24. And we can come down and look at the actual curve fit and see if we think the curve fitting has done a good job. Scrolling back here, this is the general idea for the ANOVA. You can see that this says colored by for the linear options. That means that this coloring is based on where the linear slopes are different between the groups. If we want to color it based on the kinetic options, we can see that there's a different thing that jumps to the forefront, which is this Paxi 11. When scrolling down and looking at the Paxi 11, we can see the differences that are being created for the initial velocity parameter of these curve fits. On to the second analysis that's available, we have reproducibility. So this is going to look at just the reproducibility of specific values for these technical replicates. Ideally, you would like to see things on the one-to-one line. And you can see that in both of these cases, they are indeed on the one-to-one line. These are for background corrected in a specific manner, log 2 of signal divided by background. We can switch how we deal with the background here and here. And more information of this is detailed in the paper itself. The next option we have is heat map. Heat map takes the data and then groups things based on the entire peptide array values. So in this case, we take a look at the slope value, we do this particular background correction, and we take a look at all of the things for post-wash, all of the samples for post-wash with an exposure time of 50 milliseconds on this side and post-wash on this side. So if we scroll down here, we can take a look at the grouping, and we can see that this is doing a reasonably good job of grouping these things. We have group 0s, kind of with group 0s, group 1s, grossly with group 2, group 1s. Group 2s grossly with group 2s. There are some differences here, but these are very related samples, so we wouldn't exactly expect perfect clustering. If these samples were less related, I would expect to see more definite clustering effects. But we can see the same sort of thing over on this side. The group 3s cluster will really well together, group 0s as well. So as we scroll up, our final thing is measurement reproducibility. Measurement reproducibility looks at an interesting idea. And in order to explain this idea, I have to go back to a previous visualization. So if we move over to this previous visualization of the Paxi gene, we can scroll down and we can take a look at this curve. curve, all of these values are the fluorescence of a specific spot for background and for signal, taken at a specific exposure time of 50 milliseconds. However, for this particular experiment, we also took all of these pictures at 20 milliseconds and at 10 milliseconds. And so what we can do is we can take all of these values together, similar to how we talked about the post-wash, and we can scroll down and look at a specific cycle. So we can look at cycle 140. And now for cycle 140, rather than using the specific spots here, we can utilize this slope in order to form this curved line. The idea here being that this should take care of some of the noise created by the differences in exposure times. So if we scroll over to what's called cycle slope, we can scroll down and we can see these new curve fits here and here. So we can utilize this cycle slope and compare that cycle slope values to the values for, say, 50 millisecond exposure time to see how close those things are and how well they correlate. So going back to our tool, we can see that for this sample, for an exposure time of 50 milliseconds, our measurement reproducibility was pretty good. When we use just the 50 milliseconds initial velocity, this is our range of values we got for initial velocity. When we use the cycle series, or the summation of things, this is the range we got, and these are very well correlated for this background over signal correction here. We can load in all of the samples at once, and we can see that overall, this is rather good. Now, if we move over to 200 milliseconds, what we'll see is more linear fashions here in this lower range, and more of a scatter here. So what we're seeing here is things that get to higher overall fluorescence, we get some more noise. And on the other end of the spectrum, we can see that for the low exposure time, the things that don't get very bright have a lot more noise. So the idea with this cycle series is that it provides us a nice middle ground between the extra noise created by low exposure and the extra noise created by high exposure. 50 milliseconds is what's typically used for this. However, the cycle series seems to be more accurate. Okay, and that's it for measurement reproducibility. If we want to take a look at all of these things, we can compare them between this data, which is our level 2.0.1 data, without background normalization, and our level 2.1.2 data. And we can look at all of these analyses and compare how they perform. In the interest of time, the only one we're going to take a look at is this heat map. So if we scroll over to the heat map on both of these particular things, we can see how much this background normalization affects the clustering. And for comparison's sake, we're going to take a look at the cycle slope exposure time and the post-wash, which are our most robust measures that we have. So once again, we have post-wash and we have cycle slope. So without background normalization, we can scroll down here and we can see that the clustering works reasonably well, with ones clustering with ones, zeros clustering with zeros, threes with threes for the most part. And over here, we can see that these cluster rather well with threes, twos in the regular two region, etc., etc. So now if we go over here and we've normalized the background, we can scroll down and we can look at this clustering again. On the left, we can see the clustering works reasonably well with the zeros with zeros, the ones with ones, the twos with twos, and for the most part, the threes with threes. What's interesting to note is that the zeros here cluster perfectly, the ones here cluster perfectly, the twos here cluster perfectly, and the threes here cluster perfectly, which suggests for at least this data set, the background correction has actually allowed these very similar samples to cluster together more robustly. Now this is an N of 1, so obviously we need more data and repetition to prove this. However, it is an interesting finding. And if we go ahead and look at all of these other analyses, we'll find similar results, with the background normalization generally improving the overall look of the data for the Kinome Toolbox. Thank you so much for listening to my series of videos. I hope you enjoyed.